Hi, my name is Shad, and I'm going to be your teacher and guide today for this course on software reverse engineering. So that's the technique of taking code that's already been compiled and reversing it into something that you can manipulate. So that means you might see the source code, or at least you will be able to see the assembly language and then make any modifications or understanding of what the program is doing. So this course is taught in 8 pieces. In part 1, we'll talk about numbering systems. So if you have not seen binary numbers or hexadecimal before, this will give you a great start into how you can understand what a reversed piece of software looks like. Then we'll do some experiences to get you used to the idea of software reverse engineering, the first attempts. Then we'll have a session where we compare the different tools that are popularly available. And of course, we're looking for free tools, but there are commercial ones as well. And that's this video here right now. And then we'll talk about the reading the stack feature. So this is understanding a program as it's running and doing some debugging while it's in action. Binary patching is about taking a piece of software and modifying it, even if you don't have the source code. And so you can patch things to fix errors or to maybe bypass a certain feature like a login screen or a registration screen. Recognizing code patterns will give you a more in-depth advanced feature of how you can see maybe malware and diagnose what it's doing. And then anti-debugging techniques is the ability to take a piece of software who is trying to hide from you. So this is a cybersecurity topic where we are looking at software that knows that you are reverse engineering it and you're trying to avoid that. And then finally, we'll do some fuzzing techniques. So this whole course here is about software reverse engineering. Now, the guides that are going to take us through here are from Dakota State University. So Michael Ham and Andrew Kramer are both the teachers. So let's get started with this section right now on software reverse engineering.
Again, I'm Andrew. Going to talk to you a little bit about different reverse engineering tools that are available to you here. So I'm going to sort of demo this using Ida as an example. Ida is one such tool, but I added and friends because really there's 5 or 6 different tools that all sort of do the same type of work. And I don't know, I use Ida the most, so I'm going to use that as my demo, but all of these can sort of do the same thing. So when we're looking at investigating a binary, trying to figure out what it does, all the information that you have available to you in that binary is like assembly code, right? And the data that goes with it. And what I have here is assembly code from ObjectDump, which is a tool on Linux that you might use to disassemble rather than decompile a file. And you can certainly read through the disassembled assembly code from binary and figure out what's going on, but that's going to be somewhat tricky, right? This is entirely linear. You might have hundreds, thousands, tens of thousands of lines of assembly code, and in my opinion, that's sort of hard to read and follow. There's no syntax highlighting, there's no indication other than just the memory address of what this is calling, what that function does. So you could use this to figure out what a binary is doing, but it's going to be difficult, arguably. It's also not interactive at all. So if I wanted to add comments or maybe make a note like this function, rather than being called 46FE70, I know that that's a hello world function. I want to annotate that. I don't have the ability to annotate that just looking through the linear disassembly. So for very small binaries, very small challenges, this might work. For anything larger, any real type of work that we wanted to do, this is probably not sufficient. So if we were going to imagine a better way to analyze binaries, it might help to take a step back. And rather than just looking at the assembly code and thinking about it in terms of assembly, think about it in terms of the control flow, right? Take a step back and imagine the C code or Rust code or Go code, whatever language built this assembly code. Imagine what it might have looked like in that language, and imagine the flow of execution as the program is executing. Because if we have a program like this, where maybe we do a function call at the beginning, We have an if-else statement where two different things, one or the other happens, a function at the end. Really, that's not linear, right? I mean, I guess you can work top to bottom, but there's branches. There's something might happen or something else, and it might loop back up to the top and do a routine multiple times, which isn't quite the same as this linear disassembly view. It would be helpful if we could view that code, that disassembled code, in terms of like a graph, a control flow graph, right? So if you think about what this code is doing here in terms of a graph, we have 4 nodes, and we're working from top to bottom. And in that first box up at the top, we call the begin function, then we check the condition if a is greater than 10, and then we have 2 potential branches. We have a true branch, which is in green there, and a red branch, which is false. So either b++ or b-, and then the code converges at the end, and we call the end function. So this is a much more human-friendly way to think about what the code is doing, right? So wouldn't it be neat if we could take this assembly code and sort of write these lines in these boxes and imagine the assembly code as a control flow graph? And in fact, that is what IDA and all of the other tools like it do. We take that assembly code, and rather than looking at it in that sort of linear, difficult to read form, we break it up wherever we see a branching instruction into a visual graph here. So this is really helpful for reverse engineering. What types of instructions do you suppose might produce a branch? What types of instructions might jump to a different location in the code or go somewhere else? There's a few of them. Loop, yeah, so loop, there's an assembly instruction loop. I don't often see GCC or Visual Studio produce a loop instruction, but it certainly could. What else? If statements, yeah, which in assembly would be like a jump if less than or equal greater than less than 0, not 0, carry, not carry. There's a bunch, right? Even a call instruction is sort of like a branch because we go to a different place in the code. So anywhere that IDA detects these branching instructions, it's going to break that out into different blocks. So IDA stands for the Interactive Disassembler, and this is the mascot for IDA. I don't know where this person comes from. Does anybody know the background? Oh, maybe so. Or Ada Lovelace? I wonder if it's...
Something like that.
This is Lady Ida.
Lady Ida. There you go. Okay. Yeah, so probably related to that. So you'll see that. We'll see her on their website and stuff. IDA's job is to ingest an executable, analyze the control flow, so disassemble it, look at all the assembly code therein, and build that interactive control flow graph that you can navigate through, you can annotate, you can change, and you can sort of work with. This makes RE much more fun, much less painful, in my opinion. Let's take a look at what IDA can do for us. So one of the advantages of IDA is it runs on anything, Windows, OS X, Linux. That's not true for all of the tools that I'm going to show you. So whatever operating system you like, it works on. It is also feature-rich. This is one of the tools that I think has been around the longest, at least in the public unclassified space. And it can do a lot of stuff. This is the 800-pound gorilla in the room. Extensive CPU support, so it doesn't matter if you're working with x86 or ARM or MIPS or what other weird architectures, PIC microcontrollers. Yeah, IDA supports like everything. Arduino CPUs, just about everything. It has built-in debugging capabilities. I believe it calls out to like the GDB server on Linux, and I don't know quite how that works on Windows, but the debugger is very good. It's visual, interactive. It also has really good scripting support in Python. We love Python. One of the problems here, though, is that the free version, the version that you can just download and use, does not come with scripting support. And that's a huge downside for me, at least, because I don't know, there's a lot of cool stuff that you can do with the scripting engine. In my opinion, this is subjective, the graphing engine in IDA is better than the others. You're welcome to disagree with me, but when I have been working with the different tools, I just find that to be the most comfortable. IDA has a free version that is quite usable. I think Python scripting support is one of the main disadvantages. And also, the CPU architectures are fairly limited on the free version. And the paid version is quite expensive. So at least you can get x86 on the free version. IDA also offers a decompiler. Hexrace, the company, offers a decompiler at additional cost. And I think it's like on the order of $1,000 per CPU type that you want a decompiler for. It is one of the best decompilers around, in my opinion again, but it is very expensive. So disadvantages, for an academic setting, it's hard to recommend IDA above anything else just for the cost. Like, students should know about it. This is something that they'll use in their professional life later on. If an employer is paying for it, that's great, but it is really pricey. Free version is cool, but limited. You should know there is academic licensing available. I believe that you have to email the folks at Hexrace and say what class you're teaching. You have to provide like a link to the catalog page. So IDA is pretty easy to install on Linux or Mac OS X, anything else. Basically, you download a binary, you make it executable, you run it, and it kind of runs through the install process. But it should already be pre-installed on your Flare VM. So if you want to open that up, we will be looking at maybe just one of the binaries in the Git directory. So I clicked on Git, and I'm opening up binaries here, and then fire up IDA. I'm going to start it on my local machine, just because it'll be a little bit more responsive. But everything that I'm doing here, you should be able to do in the VM as well. Once you get IDA open, go ahead and click New, and open up any of the either .exe or .out files from your binaries directory. I'm not going to actually go through reversing a binary right now, so as long as we can open something up just to look at what windows are available and features are available to you, that's all we need here for the moment. So once you have IDA open, click New, and then I'm just going to select, let's do hello world.exe. Sure. Actually, maybe I'll do hello world.out. I'll do that. So I'll open that up.
Which program is that? Is Hello World?
Yeah, I opened up the hello world.out file, but again, all we're going to do here for the next 10-15 minutes is talk through the interface, so it doesn't really matter which one.
Is that anyone?
Yeah, so depending on which executable you open, you might see different options for the type of CPU that IDA thinks that this binary is built for. Probably what you want to select in almost all cases is just meta PC disassemble all options. That will kind of cover whatever is inside of the binary and figure it out on its own. But if you knew for a fact that this was compiled specifically for an Intel 8086, maybe you would want to select that just to help IDA be a little bit more specific about the type of CPU that it thinks is in this. So I'm going to click OK. And now, I don't know if you all will see this error. When I install IDA on Linux recently, I get an error about GNU LNX x86. Do you guys know what that is? Have you seen that? I just click through it, click OK twice, and it goes away and everything's fine. So, when in doubt, just ignore the error message. So, I have IDA open here. This is the interface. And let's talk through each component. So when you open it up, this is the file load interface. You can select whatever type of CPU is being used here. One of the helpful things when you're loading a file in also is you can rebase the executable. So you can say, rather than assuming that this is going to be based at the offset, like what did you say, 40,000? 400,000? maybe if your computer is basing it at 800,000 and you want all of those addresses to look the same, you could put that in the loading window there. Other than that, I usually just click go. So here's the main interface, and let's look at each window. Over on the left-hand side, these are all of the functions that your program might use while it's running. They are color-coded. So the ones that are just plain white background are functions that are compiled into the binary itself. That's a function that exists in this binary. The ones that are in purple, or I think also blue sometimes, let's see if we have any of those on our list. Anyone want to guess what the purple, pink means here? Yeah, they're functions that exist in some other piece of code that the binary might call. So from a DLL file on Windows, a shared object file on Linux, it's an external symbol that the function is referencing. So in this case, we have like libc start main and the plits function. Those are functions that exist in the standard C library, but this binary is going to reference this. So we have our list here, and if you double click on any of these, it will seek to that function, and you can see this binary isn't terribly interesting from a control flow perspective. It just prints hello world and exits. So nothing to see beyond just one block of code there. So in the middle, we have code browser. Well, that's like the Ghidra word, code browser. I guess you could call this the code browser on IDA as well. And notice that there are tabs up at the top also. So the IDA view is going to be your graph view, but you also have a hex editor up here. If you wanted to define structures that the program might be using to make those look a little bit better in the disassembled view, you could do them here. Enums, imports, exports. So I often will use the hex editor as well. This is a little bit clunky, but if you wanted to patch the binary, you would have to press, I think, F2 to edit, and then you can change the code there, and then I think F2 again will apply that change. I'm not actually going to edit my binary here at all, but hex editor is available to you. That's nice. Something else that you should know about IDA specifically, this is an IDA specific thing, if you press spacebar, it will switch to that linear disassembly view, which depending on what you're reverse engineering can be helpful in understanding what it does. So oftentimes, graph view is going to be what you want. But I can show you some examples. In fact, maybe I'll push some binaries to the GitHub page. I can show you examples of where IDA thinks that the function ends, and actually there's some relevant or important code after it. You can sort of lie to IDA and trick it into thinking this is all of the code, when in actuality there's more. So if you wanted to see all of the code around this, you would press spacebar, and now we've switched to the linear disassembly view, a lot more like object dump, what I showed you on that first slide, and we can scroll around. And if you notice up here at the top, we have a little pointer that is moving as I scroll. So that shows me where in the binary I am as I'm seeking around. So what do you think? Do you like graph view better or linear disassembly? Also, whenever you press spacebar, it's disassembling at the current cursor position. So I've been seeking around, and notice my cursor is now in a different function. So if I press spacebar now, I go to graph view in that other function as well. If I want to get back to main, just double click main. Now we're back there too. Okay, so let's see what else we have. Helpful to know that in the bottom right, there's a little mini map of the control flow graph. So if I have a huge function, it doesn't really apply here because this thing's small enough to all fit on the screen. But if I have a huge function, I can click here and drag my window around. Oftentimes you'll be reverse engineering large binaries compiled code, and there will be like hundreds of these nodes. The graph will be so large that you can't even hardly see it. It's helpful to be able to see around there. So as I mentioned, up at the top we have the memory segment map, and these are color-coded, so you can see what the structure of the binary overall looks like as you're seeking through it. So in gray here we have data, right? If I have global variables or string constants that the binary is going to use, those are probably at the beginning of the binary up here. The blue is regular functions from the binary itself. We have external symbols. I think this would be like the GOT or the PLT. No, that's wrong. Well, anyway, you can see all of these different segments are color-coded, and as we scroll through the memory map, we can see what they are. And then down at the bottom, we have the console. This is where you would run your IDA Python scripts if you had a professional version of IDA that supports that. I'll show you one of my favorites. Just an example of the power of the Python scripting engine. There is a tool called Lighthouse. That's not what I wanted. Okay. GitHub. There's a cool picture of a lighthouse. Okay, Coverage Explorer. So if we are, say, fuzzing a program, and we want to know how much of the code we're covering with our fuzzer, like how many of those code blocks are actually being hit and interacted with, there is an IDA plugin that will allow you to ingest coverage data, and then it will change the colors of all of these blocks based on how frequently that code block was hit during execution, which is awesome. Lighthouse is a really cool tool. There are some open source clones of this, but Lighthouse is definitely best. So another thing to know about IDA is that the layout is fully customizable. You can drag and drop things really easily, so you can kind of make it look and feel like what you want. Each of those windows you can drag from the top and rearrange. So let me show you, for instance, if I decided that, I really want this hexadecimal hex editor next to the graph view, I could either drag it over one of these arrows or drag it to the side, and it will add that on the edge there. So when you close IDA, it gives you the option to save what it calls a database, an IDB file, IDA database. The IDA database is sort of a save of your work on that binary. You're not actually saving changes to the binary itself. What you're doing is saving a database of any annotations or edits that you made to it. So I'll tell you what, I'm going to make just one code comment here. I'm going to go to the main function, and right up at the top, I'm going to hit the semicolon, which if you've written a lot of assembly code is a comment. It's semicolon, brings up the comment window, and I'm going to type, Andrew was here. Put a comment there. Oh, and that actually put it right up at the top. I could also put comments next to assembly lines, like if I put my cursor here and say, this is a call to the puts function. We can save that, and that will add a comment there. If I close this now and save, so we'll go exit, and I'll say, sure, pack the database store. Now, when I go look in that folder, and what were we working with? Hello World, PDB. Okay, it's probably right in front of me. It's going to be an IDB file. Oh, I64. There we go. So that is the IDA database that stores those comments and things that I made. So if I open that binary up again in IDA now, all of those comments and changes and annotations will be saved. So if you're working on a large reverse engineering project, this is really helpful for the long term, right? You could work over a series of days or weeks or years, as I'm sure some folks do. Okay, so let's talk about some alternatives. Up here, I have 5 alternatives to IDA that do sort of kind of the same thing. They are varying degrees of open source, proprietary, paid, free. I'll talk about the advantages and disadvantages of each. So Ghidra, I think that eventually Ghidra is going to overtake IDA as the de facto reverse engineering tool, if not already getting there. This was built by an NSA years and years ago. If you look through the code, there are comments that go all the way back into the 90s. So clearly, they were working on this quite a long time ago. It was previously either secret or top secret. I don't know. But it was released open source in the last couple of years, and it is really, really good. Advantages of Ghidra, totally free. You can go look at the source code, you can build it yourself, you can use it in the classroom, use it for whatever you want. Ghidra also has a really good decompiler. Like, as good as Hexrays, maybe even better in some cases. They put a lot of work into their decompiler. Again, the difference between a disassembler and a decompiler, whereas IDA, without those extra features, is just a disassembler, the decompiler is going to give you source code. This has also made reverse engineering as a class a little bit tricky for us, because in the past, I could just give students binaries and say, it's your homework assignment to go figure out what this does. Now they throw it into Ghidra and they get all the C code, and it makes it much easier. So, I don't know. I would encourage students not to go directly to the Ghidra decompiled source code view, but it's hard to prevent them from doing that. So just be aware that in this day and age, as of a couple of years ago, that's just available, and that's, I mean, it's an awesome tool. It's good to have. Also, Ghidra lets you do multiplayer reverse engineering. Basically, so you know that I64 file that IDA saved with all of my changes in it? Ghidra comes with a server that will manage those files using version control between many users. So another tool that you might be interested in looking at is Binary Ninja. Has anyone used Binary Ninja before? Okay, so this is kind of an up-and-coming tool. Binary Ninja is a proprietary tool, but it's far less expensive than IDA, and it is gorgeous. I'll just show you real quick what that looks like. Here's Binary Ninja. We start it up. Well, maybe. Let me see if I can open a new file. Well, I won't go through everything, but it's just a much cleaner, more beautiful interface. Let me just show you what that interface looks like. So here it is. It's also pretty elegant, less feature-rich than IDA, but has all of the features that you need right there available. So I would recommend looking into Hopper if you want a more inexpensive option. So let me show you what Cutter looks like. So here's the binary browser window. Let me open up, let's see. Excuse me. So I'm going to open up the Hello World again. Hello World.out. And you can select what level of analysis you want. So if you have a large binary, several megabytes, you might not want to go up to advanced, but you'll get more data about it if you do. So I'll just click Auto, click OK. And here's the window. We will go to the entry point. And so by default, this is just showing me the linear disassembly view, but it does have graph view as well, which I can move around in. It also has the hex editor. It has the decompiler, which is, as you can see, like not great, but all right, close enough. Uses registers as variable names, and it gets you there, right? It's pretty close. I have one more slide here. Ah, yes, of course. We must talk about Radare2, Radare2. This one is awesome. 3 stars. It's great. 3 stars out of 3. So if you love working in the terminal, this is an awesome tool. If you don't like typing all of your commands out, probably not going to be for you. It takes some getting used to. I will readily admit I am like an amateur at this. You could probably school me on how this thing works. But I'm going to do my best attempt to show you what this looks like on the command line. So let's go to desktop. Let's go to that folder. Here. Okay, I'm going to open up the O3 Hello World.out using R2. This should work on Kali for you. I think that Kali has R2 built in. So when you start it up, you get this. By default, it hasn't performed any analysis on the binary because depending on how large it is, that might take like hours, right? So you can tell it how much analysis you want it to do by how many A's you give it. I usually give it 3 or 4 A's. How many A's do you give it when you? 3? Okay, we'll start with 3 A's. So it performs some basic analysis. And I love this. It's kind of a humorous tool. If you provide too many A's, it says a developer is coming to your place to manually analyze the program. Hilarious. this tool's wonderful. So, we can do things like show me all of the analyze functions in a list, I think is what that would stand for, AFL. So here's all of the functions in the program. I'm going to tell it to go to the address of debug.main, so I'll seek to dbg.main. I don't expect you to be following along, because I want to show you what this is doing. And notice that the pointer in the binary has changed here now. And then I could tell it, like, print the disassembly of this function, and it will show me a nice color-coded disassembly there. And then, even better, I can say VV, like go into visual mode, very visual mode, I don't know, and it will show me a graph view that I can browse around from the command line as well. I can quit back out of that to hex editor view, quit back out of that here. This framework is incredible. There is so much stuff built in here. It's awesome. It's all free. It's open source. Disadvantage, it changes constantly. Good question. So Radare2 has a scripting engine called R2 pipe, which basically is language bindings that allow any language to send and receive commands and data from this interface here. So I'll tell you what, I will show you an example from my reverse engineering class. We do a module on scripting, and I have, okay, so here's an R2 pipe Python script. There are language bindings for C++, Go, Java, whatever language you want to program in, you can probably import R2 pipe and make it work. Let's see if I can make this a little bit bigger. So here's what it looks like. So you would import the library. This one that I wrote specifically is to find dangerous functions within a file. So we're looking for things like string copy, string cat, gids, things that might have overflows or integer signedness issues. And the syntax here is you just say r2pipe.open, provided a file, and you can provide it command line options for opening that file. And then you just say r.cmd to send the command. So here I'm saying analyze. I use 2 E's rather than 3 or 4. And then you can just write send and receive commands and data as if you were typing those. One of the other cool things that it does is JSON input and output. Do you all know what JSON is? JSON. So rather than just getting the output of the AFL command and having to parse that as lines of data, you can say r.command j, and then most of these commands support putting a j at the end. And let me show you what that looks like in R2. So if I start this up again, I do AFL, this is my human readable list. If I say AFLJ, it gives me JSON of the same thing, a JSON object. And so when you then use Command J in Python, this will give you an object that has all of the dictionary annotations, easier to work with. More cool things that this does. It is fully discoverable from the command line. So if I don't know what to do, I say question mark. And it shows me, here's all the commands that you can run. So I used an AFL. How did I figure that out? Well, A is for analysis. So if I want to see what types of analysis it can do, I can say a question mark. Now it shows me all of the different types of analyses it can do. So if I want to analyze a function, well, how can I analyze functions? AF question mark. And so now I can see here, wait, where is it? There it is. List functions, right? So it's fully discoverable. Another cool thing that it does is it lets you do like a grep search from the command line here. So if I do tilde list, it shows me only lines that contain the word list. So the command line interface is really powerful. For it to be a disadvantage that it's a command line interface, it's purely based on your style, right? What you want. So I really like this tool. It's hard to use unless you have lots of practice with it, but super powerful.
So given that things like Ghidra will give you a very good decompiled version, so what's the like the students will ask, what's the value of learning disassembly if I can get
It
everything with Ghidra?
changes what reverse engineering looks like and what the task is. So prior to decompilers being available, it seems to me that the task of reverse engineering was really reading assembly code and figuring out what the program does, right? Now that we have decompilers, it's pretty easy to just decompile and go, oh, it's an if statement with a for loop. I can see that. But none of the variable names are going to be intact. Structures, which are used ubiquitously throughout real professional proprietary software, none of those data structures are going to be defined. So Ghidra might say, oh, I'm writing to 25 different variables, when in actuality, you're just copying the structure into memory. And so like the reverse engineering process in the Ghidra world is defining all of the variable names and structures and different things around what the program does to make it look beautiful. It really brings up the question of like, do students still need to spend a long time looking at pure assembly code or not? Thoughts on that?
I mean, I think so, just because,
I'll give a very specific example of exactly what you just said. The Ghidra decompiler will completely eliminate anything that it thinks is dead code. So if you have an if statement that is always a false condition, or just code that is never reached, it just won't even show you that in the decompiled output. But if the function does some tricky calculation at runtime that ends up calling that dead code, and it's actually live code, that should have been seen. And so seeing that actual truth, what's actually in the binary versus what Ghidra thinks it might have looked like, is important. And driving that point home for students is a challenge, right? Because they just look at the C code and go, oh, look, there it is.
So is it true that we're kind of making the assumption that the primary use case of reverse engineering is to look at a piece of malware and figure out what they're trying to accomplish?
I mean, that's oftentimes when it's going to be used. I would say reverse engineering is also really useful for programmers. If you are, let's say you're building a Linux driver for a graphics card, and that company only releases a proprietary compiled version of their graphics software, you want that to work on Linux, but there's no driver available, they reverse engineer those software tools to build the open source graphics card driver, right? If you're, like for students, game hacking is something that gets them excited. I would tell a student, like, look, if you want 1 million gold coins, that's just an integer somewhere in memory. If you can figure out where that integer, counting up your amount of gold in the game is, then you can hack the game, right? So I think there's more use cases than malware. That is
I think malware is kind of the big direction this goes, but like Andrew said, it's not the only result you can have from malware or from reverse engineering. I'll post a graphic or bring it up. There's an idea called the funnel of fidelity. It's an idea by Spectre Ops. And the idea is that when we ingest like tens of thousands of events from our endpoints in a network, right, we have some automated tools and what the EDRs are reporting back, and we can start to get some indicators of like, is this a real compromise? Is it something important or not? And the idea of the funnel of fidelity is by using these automated tools, narrowing down false noise, things like that, we eventually get to the point where somebody from the network team has to take a look at it. And if that person realizes like, yes, this may be an infection, this may be malware, then they hand it off to someone that's going to do some actual manual hands-on keyboard RE on that. So it's when you get to that point of like, we have a pretty well confirmed compromise of some sort, we need to figure out that, what really happened. That's kind of where that skill set fits in.
Why would you go through that reverse engineering approach instead of kind of like doing some kind of falsing and then just like giving it some inputs and then observing the outputs?
You
like
can
in
be
a sandbox?
much faster with reverse engineering.
Okay.
Like if you have the skills to open up IDA and look at what it's doing, you can know immediately what it does versus it might take you months of providing data and watching.
Random.
And you might never even hit the thing that it's meant to do. Right? Like a lot of times, really, really targeted malware these days, the stuff that red teams are doing and nation states are doing, they will add code to the malware that says this should only run if the domain name is X and the username is Y and the computer serial number is Z. Like they get it down to that level. In fact, I think is it Stuxnet had like a hash in it of several of those things together, and they couldn't figure out initially like what the inputs needed to be to make it run. And so that's something that you would just never stumble upon via fuzzing. But with reverse engineering, we look at a few lines of assembly and go, ah, there it is.
Gotcha.
That's what it does. Saves a lot of time.
Yeah. And you mentioned IDA also does that kind of fuzzing, like the plugin you showed us, Lighthouse plugin.
Oh, Lighthouse. So Lighthouse is only for coverage. Lighthouse doesn't do the fuzzing itself, but if you've been fuzzing and it's been a few days and you have a queue of files that you're fuzzing, modifications you're making, and you want to see, does this new file that I generated cover this function or reach this path, or how does it go through this series of if statements? You plug that back into Lighthouse, and it's going to show you in a visual way what it actually did.
Gotcha.
But that's IDA Python. You have to have the pro version.
Right.
Unfortunately.